to x3. Whenever you assume x2 is equal to k, x3 is equal to k, and x1 is already 0. So the eigenvector corresponding to lambda is equal to 2 is 0, 1, 1. Now put all these eigenvectors in column, in matrix, in column of the matrix. So what is our first eigenvector corresponding to lambda is equal to 0, 0, 1, minus 1. So that is our first column of the matrix P, 0, 1, minus 1. What is our eigenvector corresponding to lambda is equal to 1, 1, 0, 0. So that is our second column of the matrix P, 1, 0, 0. What is our eigenvector corresponding to lambda is equal to 2, 0, 1, 1. So that is our third column of the matrix P. Okay. So this matrix P diagonalizes A, and now P inverse AP. If you want to find P inverse AP, P inverse AP is always triangular matrix in which the main diagonal elements are exactly the eigenvalues of the given matrix A. So this P inverse AP is equal to what are our eigenvalues? 0, 1, 2. So you can see in main diagonal elements we have 0, 1 and 2. Other all elements are 0. So that is our P inverse AP. If you want to check, that is homework for you, that you have already P. You can find P inverse, that how to find inverse of the 3 cross 3 matrix, that you already know. So you have P inverse now. You have A, matrix A, and you have P. Multiply this 3 cross 3 matrix, you will get again 3 cross 3 matrix, and that is exactly this matrix 0, 0, 0, 0, 1, 0, 0, 0, 2, that are triangular matrix. And I again repeat that the in main diagonal elements we have exactly the eigenvalues of the given matrix A. Okay, so this question is complete now. Next question. Question 3 C. Determine whether B is in the column space of A, and if so, express B as linear combination of column vectors of A, where A is equal to 1, minus 1, 1, 9, 3, 1, 1, 1, 1, and B is equal to 5, 1, minus 1. This question asked in 3 marks in this question paper. So what is our question? Again I repeat that you have to find that B, determine whether B is in the column space of A, and if so, express B as a linear combination of column vector of A, where A and B are given. Now we reduce the augmented matrix A oblique B to an echelon form. We know that one theorem, that B is in the column space of A if and only if Ax is equal to B is consistent. There is one theorem that the column vector B is in the column space of the given matrix A if and only if Ax is equal to B is consistent. The system of linear equation Ax is equal to B is consistent. So instead of we have to check that B is in the column space of A, what we have to do, instead of that one, we just check Ax is equal to B is consistent or not, and exactly that we have to do here. We check that Ax is equal to B is consistent or not. That means Ax is the linear system of equation Ax is equal to B have solution exist or not. Okay. So we reduce the augmented matrix A oblique B to an echelon form, that is augmented matrix, first matrix is A and the second is a column vector. First is 1 minus 1 1 9 3 1 1 1 1, that is our matrix A oblique column vector 5 1 minus 1. Now we convert this matrix into a row echelon form, and now I hope that you know that how to convert any matrix into a row echelon form. I again repeat all the conditions of row echelon form, that in row echelon form you just see in the first row non-zero element. That non-zero element is exactly our leading entry of the first row. Below that leading entry all the elements should be 0. All the elements are 0. Now see second row. Again second row, the first non-zero element is our leading entry. Below that leading entry all the elements should be 0. Okay, so that is our first condition, that below the leading entry in all the row all the elements should be 0. Now next condition for row echelon form, that leading entry, whenever we are going from above to below, the leading entry goes from left to right. Okay, it's not goes from right to left. The leading entry is goes from left to right whenever we are going from above to below with row wise. Now if there is any 0 row, it should be the bottom of the matrix. If there is any 0 row means all the elements are 0 in that particular row, so that row should be bottom of the matrix, right? So these three conditions are satisfied, then we can say that the given matrix is in the row echelon form. Now to convert reduced row echelon form, we want two more conditions. Definitely these three conditions should be satisfied. Two more conditions are added in these three conditions. So first condition is the leading entry must be 1. Okay, the leading entry must be 1. And the second condition, in that leading entry all the elements which are below of that leading entry should be 0. That we know, that is the condition for row echelon form. But in reduced row echelon form, all the elements from the leading entry below and above, both in column, in particular column in which have leading entry, except that leading entry all the elements should be 0. That means below and above all the elements are 0. Okay, so these two conditions are added to be a reduced row echelon form. Okay, so now you can understand that how we convert this matrix into a row echelon form. We have augmented matrix A oblique B 1 minus 1 1 5 9 3 1 1 1 1 1 minus 1. We are converting this matrix into row echelon form, so that's why we multiply first row with minus 9 and add into the second row. We multiply first row with minus 1 and add into the third row. So here is the process. We multiply first row with minus 9 and add into the second row. So the first row is as it is 1 minus 1 1 5. Second row become 0 12 minus 8, because we are multiplying first row with minus 9. Okay, so you can see from the first matrix 9 minus 9 0, 3 plus 9 that is 12, 1 minus 9 that is minus 8, and 1 minus 9 into 5 that is minus 45, so minus 44. So that's why this second row becomes 0 12 minus 8 minus 44. Okay, now we multiply first row with minus 1 and add into the third row. So just R3 minus R1, so that's why you can see 1 minus 1 0, 1 plus 1 1 plus 1 that is 2, 1 minus 1 0, and minus 1 minus 5 that is minus 6. So the third row become now 0 2 0 minus 6, 0 2 0 minus 6. Okay, now next process, we are just interchanging the second and third row. Okay, so the first row is as it is 1 minus 1 1 5. The second row become now 0 2 0 minus 6. The third row is 0 12 minus 8 minus 44. Now we are multiplying second row with minus 6 and add into the third row. So the first and second row are as it is, 1 minus 1 1 5. The second row is 0 2 0 minus 6. The third row become 0 12. We are multiplying second row with minus 6, so 12 minus 2 into 6, that is 12 minus 12, that is 0, minus 8 minus 0 into 6, that is minus 8, minus 44 minus 6 into minus 6, that is plus 36. So minus 44 plus 36, that is minus 8. So that's why third row becomes 0 0 minus 8 minus 8. Okay, so this matrix into row echelon form. Next process, we are just dividing second row with 1 by 2, just because of our leading entry become 1 now. Okay, no other reason for that. So we are multiplying second row with 1 by 2 and multiplying third row with minus 1 by 8. So the first row is as it is, 1 minus 1 1 5. The second row become, we are multiplying second row with 1 by 2. So the second row become, you can see 0 2 by 2, that is 1, and minus 6 by 2, that is minus 3. So 0 0 as it is. So 0 1 0 minus 3, and the third row become, we are multiplying third row with minus 1 by 8. So that's why our third row is now 0 0 1 1. So now this matrix into a row echelon form. Okay, and now you can see the Ax is equal to b is consistent or not. We are just taking these equations, that x minus y plus z is equal to 5 from the first row. In the first row we have 1 minus 1 1, so x minus y plus z. The first column is for x, the second column is for y, third column is for z. So that's why x minus y plus z is equal to 5, then y is equal to minus 3 and z is equal to 1. So we will get the solution. So basically we will get all the values of x, y, z. That means Ax is equal to b is consistent. Okay, Ax is equal to b is consistent. That means what? B, we can express b as a column space, as a linear combination of the column vector of A, and b is in the column space of A, definitely, because of Ax is equal to b is consistent. Okay, these two part are simultaneously, right? Ax is equal to b is consistent, and another words is b is in the column space of A. Okay, these two statements are equivalent using one theorem. So x minus y plus z is equal to 5, y is equal to minus 3, z is equal to 1. Put the values of y and z in the first equation, you will get x is equal to 1. So b is 5 1 1. You can see b is 5 1, it's 5 1 minus 1, that is equal to 1 into first column of the matrix A, 1 9 1. Okay, that is x is 1, minus 3 into the second column of the given matrix, that is minus 1 3 1, and the 1 into the third column of the given matrix, that is 1 1 1. Okay, so this question is complete now, and the answer is b is in the column space of the given matrix A, and we can write the column vector b in this method. Okay, so next question. Question 4a. Let R2 to R3 be defined by T of x1 x2, that is equal to x1 plus 2x2 minus x1 0. Find the matrix T from B dash to B with respect to the basis B, where B is u1 u2 and B dash is v1 v2 v3, where u1 is equal to 1 3, u2 is equal to minus 2 4, v1 is equal to 1 1 1, v2 is 2 2 0, and v3 is 3 0 0. So first we have to find matrix T from B dash to B. For that, second we have to verify this term, that matrix T from B dash to B, matrix X corresponding to basis B, that is equal to matrix T of X corresponding to basis B. holds for every vector x, x1, x2. So just try to prove first part, or just try to find the first part, t of x1, x2. Okay, t of x1, x2 is equal to x1 plus 2x2 minus x1, 0. Now try to find t of u1. What is our u1? u1 is 1 and 3. So t of u1 is t of 1, 3. Just put instead of x1 in this definition, t of x1, x2 is equal to x1 plus 2x2 minus x1, 0. In this definition, just put instead of x1, 1 and instead of x2, 3. So you will get t of u1. T of u1 is equal to t of 1, 3, that is equal to 1 plus 2 into 3, that is 1 plus 6, that is 7. Then minus x1, that is minus 1 and 0. Similarly, you can find t of u2. T of u2, that is t of minus 2, 4, that is equal to, instead of x1 we take minus 2 and instead of x2 we take 4 in this definition. So minus 2 plus 2 into 4, that is minus 2 plus 8, that is 6, minus of minus 2, that is 2, and then 0. So we will get t of u1 is 7 minus 1, 0. T of u2 is 6, 2, 0. Okay. Now what we have to find first, we want to find t of, just try to understand the question properly. We want to find the t of the matrix T from B dash to B, right? So here is the t of u1 and t of u2. Now let 7 minus 1, 0, that is t of u1. 7 minus 1, 0 can be expressed as linear combination of basis vector of B dash, that is 7 minus 1, 0, that can be expressed as linear combination of basis vector v1, v2, v3, where v1, v2, v3 are basis vector of B dash. So 7 minus 1, 0 is equal to a v1 plus b v2 plus c v3, that is a into 1, 1, 1 plus b into 2, 2, 0 plus c into 3, 0, 0, that is equal to a plus 2b plus 3c, then a plus 2b, then a. Okay, this gives a plus 2b plus 3c is equal to 7. A plus 2b is equal to minus 1. Just comparing the left and right part. Left side we have 7 minus 1, 0, and right side we have a plus 2b plus 3c. So you can comparing a plus 2b plus 3c is equal to 7, a plus 2b is equal to minus 1, and a is equal to 0. Put a is equal to 0 in the second equation, you will get b is equal to minus 1 by 2, and put the values of a